For Lab 4, we're going to be looking at the percent water in a hydrate.
Let's start by looking at the definition of a hydrate. So a hydrate is a solid compound, usually in a crystalline form, in which a definite amount of water molecules are trapped in the crystal arrangement. So let's look at this chemical formula of copper 2 sulfate hexahydrate. So notice, this is a solid. Also notice, it has 5 water molecules. So that means for every 1 copper ion and for every 1 sulfate ion, there are 5 water molecules in that crystal structure, in that lattice arrangement. So I have an example shown over here to the right in this white box. So copper, it's copper 2 sulfate, so it's copper 2 plus ion. Then we have the sulfate ion over here with a 2 minus charge. So for every 1 copper ion and for every 1 sulfate ion, we have 5 water molecules. And you can count the water molecules that we have here too. So there's 1, there's 2, 3, 4, and 5. So I said in the definition that those water molecules are trapped. That's a little misleading. They're not exactly trapped within the crystal lattice. They're actually held in place in this hydrated compound by electrostatic forces between the polar water molecules and the ions themselves. These electrostatic forces are weaker than the ionic bond between copper ion and the sulfate ion. So since these electrostatic forces are weaker, what we're going to do in the lab today is we're actually going to drive off those water molecules. So we're going to try to make the hydrated compound an anhydrous compound. Anhydrous meaning with no water, dry. So our goal is to get these water molecules out of the crystal structure.
So let's look at how we name hydrated compounds, because you'll see on the pre-lab portion for number 5 on page 27, you are given 2 examples of hydrated compounds, and the question asks you to give the correct chemical name for the following compounds. So in order to name hydrated compounds, it's very similar to just naming ionic compounds. You want to start by naming the ionic compound first. So out of this chemical formula, the ionic compound is this CuSO4. So how do you name that? Well, a little refresher. Notice that Cu is copper, and copper is a transition metal. So with transition metals, they have variable charges. What that means is copper could be a +1 or a +2. So looking at the formula itself, I don't know which copper ion I'm looking at. So when I name it, I need to first figure out what the charge on copper is, what its oxidation state is, so that I can include that when I'm naming the compound. So how do I figure out the charge on copper? Well, you use what it's attached to. So what that means is we're going to look at the sulfate ion. So the sulfate ion, SO4, when I look that up in my polyatomic tables, I see that SO4 has a charge of -2. Now this compound as a whole needs to be neutral. So what that means is if I have a -2 charge on the anion side, then I'm going to need a +2 charge on the cation. So I'm looking at the copper 2+ ion, because now the 2+ will cancel out the 2- and equals 0, making the compound as a whole neutral. So now that I know which ion I'm looking at, I can go ahead and name. So it's the copper 2+ ion, so I would write copper and then Roman numeral 2 to indicate that the ion I'm looking at is the 2+ ion. To name the polyatomic it's attached to, SO4, I just look at the polyatomic tables, and SO4 is sulfate. So this would be the correct name for the ionic portion of this hydrated compound. Next, I need to include the water molecules, because notice there are 5 water molecules in this chemical formula. So to write the water molecules and to name those, all you need to do is write prefix for the number. So in this case, we have 5 water molecules. So I would look up the prefix for 5, which is penta, and then just write the words hydrate after the prefix. So for the water molecule portion, it's going to be pentahydrate. Notice I made a mistake here. I wrote hexa. That is incorrect. Don't do the same thing I did. Hexa would be the prefix for 6, and we want to use the prefix for 5, so it's pentahydrate. Make sure you are correcting that and writing pentahydrate. So the overall name, now you just put them together. So copper 2 sulfate, and then not hexahydrate, but pentahydrate, since there are 5 of them. All right, so I have named one for you on number 5 of your pre-lab. So the other one you have to name is the sodium sulfate compound with the 10 water molecules. Don't make the same mistake I did and get the correct prefix for 10.
So we're going to do this same thing, but with an unknown hydrate. So first what we need for our apparatus is a ring stand with an O-ring. You can see in the picture to the right. On top of that O-ring we have a clay triangle. This is going to be used to set our crucible in. So you'll notice there's a crucible over down here in the corner, so this is a crucible, and then there's also the cover, which is kind of blurry, kind of hard to see, but there'll be a better picture of it in a second here. So we also need a crucible tongs. So this is a special tong to pick up the crucible because we are going to be superheating it, and it's going to get very hot, so we definitely don't want to touch it with our fingers. So we'll use that tong to take it off of the clay triangle, and we're going to set it on this wire mesh cooling pad. We also need a Bunsen burner to do the heating. So let's go to page 35 of our lab manuals and start collecting some data for the data table. So we are going to be using unknown number 1. So that's our sample identification number. The first thing we need to do is mass the crucible and the cover. So the mass of the crucible and the cover when it is clean, dry, and empty is 34.546 grams. So why are we measuring the crucible and the cover? Because when we're heating this, we're actually going to have the crucible cover on top at a slight angle so that the water molecules can escape, but we're not losing any of the solid, any of the ionic compound that we want to keep. So next we'll take our unknown, look at those pretty white crystals, and we will add, according to the lab manual, 2 to 3 grams of the hydrate sample. So once we add it, we of course need to mass the crucible, cover, and hydrate. So this 36.887 grams is all 3 of those together. So you would put that under trial 1. Next, we need to strongly heat it. So in order to strongly heat it, we light our Bunsen burner and we want to have a blue flame. You can see the blue flame to the left, and what we're looking for is to get this inner cone. So you can kind of see the outline of this cone. That's the hottest part of the flame. So we want to heat the crucible to get that blue cone very, very close to the bottom, but not necessarily touching. Okay, so we're not looking for a red flame, blue flame's hotter. So you can see in the picture to the right, once I started heating it, we heat it so strongly that the bottom of that crucible turns red. So here we are heating up the hydrate. We're trying to drive the water out of those crystals. You can see we have the crucible cover on top of the crucible, but with a slight gap. That's to allow the water vapors out.
we need the crucible cover on because the crystals, the water, is trapped inside of those crystals. So when we're heating it this strongly, what's going to happen is it's going to break those crystals apart. So there's going to be some popping. And we don't want to lose any of that material to get a more accurate mass at the end. So we put the crucible cover on for any of the material trying to pop out will get stuck on the crucible cap. This is why when we masked the crucible when it was empty, we included the mass of the lid as well. So you can see we have the crucible in the clay triangle. We are heating it with a Bunsen burner. And if you look at the bottom, I'm heating it strongly right now. So you can see how the bottom of that crucible is red hot. It's needed to get it that hot in order to drive off those water molecules. And since this is an inorganic compound, its melting point is very, very high, so we can heat it this strongly without doing any damage to the compound itself. So we're going to continue this for 15 minutes, and then you will see what the remains look like. It's going to look a little different. It's not going to be as crystalline, and you'll also get the mass for it as well. When we're ready to take it off, we're going to turn the gas off. We are not touching the crucible. Instead, what I'm going to do is I'm going to use this crucible tongs over here. Notice it has a little curve in it so that it can pick up the crucible nicely. So I will transfer both the crucible and its lid onto that wire mesh gauze. I don't want to set it directly on the countertop because it'll be so hot it might break. So I'll put it on that cooling pad. Once it's cool, I will then mass it, and you'll see those results.
So after the heating process is complete, this is what our anhydrous ionic compound looks like. So no more water molecules. We are not looking at the hydrate anymore. We are now looking at the anhydrous ionic compound. So once it is cool, we need to mass it. Once again, making sure to mass the crucible cover as well in case there's any material on the crucible cover. And because we masked the crucible cover at the beginning, so we want to include it here as well to keep our data accurate. So the mass of the crucible, the cover, and the dry solid was 36.533 grams. You'll notice next you need to calculate the mass of the anhydrous compound. So remember, anhydrous just means without water, dry. So in order to do that, you need the mass of the crucible with the cover. Because remember, what we do with the words, we're doing with the numbers. So what do I mean by that? In order to calculate the mass of the anhydrous, you need the dry solid by itself, because dry solid and anhydrous is the same thing. So to get the dry solid by itself, we need to subtract out the mass of the crucible and cover. And that's what this number here, the 34.546, represents. It represents just the crucible and cover. So if we subtract these two numbers, we will be left with just the dry solid, the anhydrous compound. Next, we need to calculate the mass of the water in the hydrate sample. So in order to calculate the mass of water in the hydrate, we need to subtract out the ionic compound. So let's look at the previous example that we saw with the copper 2 sulfate pentahydrate. So we need to take the hydrate, the mass of the hydrate, and subtract out the mass of just the ionic compound, so the anhydrous. That will leave us with the mass of just the water. Okay, so what that looks like is we're taking the mass of the hydrate subtracted by the mass of the anhydrous to get the mass of the water. Remember, mass of the hydrate, that's the mass of before we started heating. The mass of the anhydrous we just calculated, and then that will give you the mass of water.
So now that we have the mass of water in the hydrate sample and the mass of the anhydrous compound, we can go ahead and calculate our percent water in the hydrate. So we're first going to be calculating the percent water in the hydrate from our data. So to do that, using your data, you want to take the mass of the water that you just calculated on the previous slide and divide it by the mass of the hydrate. This is the mass of the hydrate before heating. Once you divide those two, you then multiply by 100 to get it in a percent form. So the reason we are calculating the percent water in the hydrate is because we're trying to identify what the unknown hydrate is. So in order to do that, we need to compare our results, our percent water, to the possible unknowns. So what you'll see underneath calculating the percent water in the hydrate sample are 4 unknowns that I have listed here. Now, these 4 unknowns are barium chloride, dihydrate, zinc sulfate, heptahydrate, magnesium sulfate heptahydrate, and magnesium chloride hexahydrate. So what you're going to need to do in order to compare is calculate the percent water for each of those possible unknowns. Because it doesn't give you the percent water of each, you'll need to calculate that before you make your comparison. So let's look at how we're going to calculate this. So to calculate the percent hydrate using just the formula, because we don't have any data for these following hydrates, in order to do that, your first step is to calculate the formula mass, including the water molecules. So we've done this in a previous lab. So to calculate formula mass, you take the number of atoms of each element present in the compound and multiply it by the molar mass that you can find on the periodic table. Now you want to make sure to include the water molecules. So the example that we're going to work through right now is lithium nitrate trihydrate. So start by making a list of all the elements in that compound. So first we have lithium. How many atoms of lithium? Well, there's no subscript after lithium, so it's just 1 atom. We're going to multiply that by its molar mass that we find on the periodic table. So looking up lithium on the periodic table, we see that its average atomic mass is 6.94. The next element present in the chemical formula is nitrogen. There is also only 1 atom present of nitrogen. Looking up its molar mass on the periodic table, we see that it is 14.01. Next we have oxygen, but notice oxygen is in more than one place. So we have 3 oxygens in the nitrate polyatomic, but we also have an oxygen in the water. And remember, we need to include the water in this calculation of the formula mass. So this coefficient of 3 in front of the water molecules can be distributed. What that means is there are going to be 6 hydrogens. We take that coefficient of 3 and multiply it by the subscript of 2. So there's 6 hydrogens and then 3 oxygens. So that gives us total oxygens of 6. We get 3 from the NO3 and then another 3 from the water molecules. So we take that total of 6 atoms and multiply it by the molar mass of oxygen, which is 16 on the periodic table. Last but not least, we have hydrogen. There are 6 of those because we have 3 water molecules and each water molecule has 2 hydrogen atoms. 3 times 2 gives us 6, multiplying by 1.008, which is the molar mass of hydrogen on the periodic table. So we multiply all of that across and get a total formula mass of 123.0 grams per mole. So next what we need to do is calculate the formula mass of just the water portion, so just those 3 water molecules, because we're trying to figure out the percent of water in this hydrate. So we need the molar mass of just the waters. So since there are 3 waters, we have just hydrogen and oxygen present, 6 total hydrogens, because there are 3 water molecules and 2 hydrogens per molecule. Multiplying that by the molar mass of water, there are just 3 oxygens, because there's only one oxygen per water molecule and a total of 3 water molecules, multiplying that by 16 to get a total of 54.05 grams per mole. So now the next step is to figure out the percent water. So how are we going to do that? Well, we're going to take the formula mass of the molecule as a whole, that 123.0, and the formula mass of just the water molecules and divide them. So to get the percent of water, formula mass of water, so that 54.05, divided by the formula mass of the entire hydrate, 123.0. Don't forget to multiply it by 100 to get it in a percent. So when we actually plug those numbers in, you can see that the percent we get for this particular compound, lithium nitrate trihydrate, is 43.94%. So you'll need to do those calculations for each one of these compound hydrates shown here. So you'll do it for the barium chloride dihydrate first, calculating the formula mass of that entire compound as a whole. Then you will calculate the formula mass of just the waters, the 2 water molecules, divide, multiply by 100, and figure out the percent. Once you have completed that for all of the all possible unknowns, compare what you got with your experimental data to the percentages calculated here, and then identify which unknown you have. Once you identify the unknown that you have, you will write it in the blanks provided and then calculate the percent error for the experiment. So to calculate percent error, remember these are absolute value signs, so you're going to get a positive number. Percent error is experimental minus actual and then divided by actual. So what's going to go in these spaces? For the experimental, that's going to be the percent of water that you calculated using your data, the actual experiment itself. The actual is the percent water calculated using the formulas. So out of those 4 choices on the previous slide, whichever one matched your experimental the most, you're going to take that percent and plug it in to the actual portions of the equation. Multiply by 100 to get it in a percent. Now remember, with percent error, the lower the percent error, the better. So you should be getting a very small number, under 5%. If you are somehow getting in the 80s or 90%, the calculation went wrong somewhere. You can always reach out to me and we will figure out what happened. Let me know if you have any questions.